September 15, 1940. RAF Fighter Command Operations Room, Bentley Priory, England. Air Chief Marshal Hugh Dowding watched the plotting table where Women's Auxiliary Air Force officers moved markers representing German bomber formations approaching southern England. The markers appeared on the table minutes before the aircraft were visible or audible, sometimes 20 minutes before, sometimes more. Radar stations along the coast were detecting the raiders at ranges exceeding 100 miles, giving Fighter Command precious time to scramble interceptors and position them for attack. This morning's raid was massive. Over 200 German aircraft bombers escorted by fighters were crossing the channel in multiple waves. The radar plots showed their positions, altitudes, and approximate numbers. Dowding's controllers used this information to vector Fighter Command's outnumbered squadrons to intercept the raids at optimal positions. The British fighters would climb to altitude and position themselves ahead of the bombers rather than chasing them from behind. This was the Battle of Britain's crucial advantage, though few outside the highest military circles understood it. German planners had calculated that the Luftwaffe's numerical superiority would overwhelm RAF Fighter Command through sheer attrition. What they hadn't accounted for was that radar allowed the outnumbered British fighters to be in the right place at the right time, intercepting raids rather than flying fruitless patrols over empty sky. Just 5 years earlier, radar had been a theoretical concept discussed by scientists in academic papers. The idea that radio waves could detect aircraft at ranges of 100 miles seemed like science fiction to most military officers. Yet in those 5 years, a handful of pioneers, physicists, engineers, and visionary military officers had transformed radar from laboratory curiosity to operational capability that would change air warfare forever. The story of how radar pioneers changed air combat is a story of scientific insight meeting military necessity, of technology developed under desperate urgency, fundamentally altering the balance of power in the air, and of innovations created in Britain, America, and Germany that would eventually spread to become standard equipment on aircraft worldwide. It's also the story of how a technology could shift the advantage from offense to defense and back again in the span of months as each side developed new capabilities and countermeasures. The concept of using radio waves to detect objects wasn't new in the 1930s. Scientists had understood since the early 1900s that radio waves could reflect off conductive objects. Guglielmo Marconi, the radio pioneer, noted as early as 1922 that radio waves reflected from ships interfered with radio communications. In 1904, a German engineer named Christian Holzmeier demonstrated a device he called the telemobiloscope that could detect ships using radio reflections, though his invention attracted little commercial or military interest. Through the 1920s, various researchers in multiple countries experimented with radio detection. In the United States, scientists at the Naval Research Laboratory noticed that aircraft flying through radio beams disrupted the signals. Similar observations were made in Britain, France, Germany, and elsewhere. But these were observations, not practical systems. The gap between noticing radio reflection and building useful detection equipment was enormous. The technical challenges were formidable. First, radio transmitters of the 1920s and early 1930s were relatively low-powered compared to what radar would require. The transmitted signal had to be strong enough that the tiny fraction reflecting back from a distant aircraft could still be detected, above background radio noise. This required transmitters orders of magnitude more powerful than typical radio stations. Second, the reflected signal's echoes were far weaker than the transmitted signals. A radio transmitter might output thousands of watts, but the echo from an aircraft 50 miles away might be less than a millionth of a watt. Detecting these faint echoes required extraordinarily sensitive receivers that could amplify weak signals without being overwhelmed by the much stronger transmitted signal. Third, the timing requirements were extreme. Radio waves travel at the speed of light 186,000 miles per second. An aircraft 50 miles away would reflect radio waves that took about 0.00054 seconds to make the round trip. Measuring these tiny time intervals required electronic circuits that didn't exist in the early 1930s. The development of radar required parallel development of high-speed electronic timing circuits. Fourth, the directional requirements were demanding. Detecting an aircraft wasn't enough. Operators needed to know where it was. This required antennas that could determine the direction from which reflected signals arrived, or the ability to aim radio beams in specific directions and scan across the sky. Antenna technology of the early 1930s wasn't adequate for these requirements without substantial development. British research into what would become radar began in earnest in 1935, driven by military necessity and enabled by scientific advances. The Air Ministry recognized that Britain was acutely vulnerable to air attack from continental Europe. Aircraft could reach London from Germany in under 2 hours. Bombers could strike with little warning, and the existing air defense system was inadequate to stop them. The air defense system in 1935 relied on several components, all inadequate. Visual observation posts along the coast could spot approaching aircraft, but only in clear weather and only when aircraft were close enough to see. Acoustic detection devices, essentially large concrete sound mirrors, could detect aircraft by their engine noise, but only at ranges of a few miles and only when weather conditions were favorable. By the time aircraft were detected by existing methods, it was too late to scramble fighters and intercept them effectively. The problem was made worse by geography. Germany's bomber bases were close to Britain. The short distance meant that even if German bombers were detected immediately upon takeoff, Fighter Command would have minimal time to respond. And Britain's fighter strength was limited. The RAF couldn't maintain continuous patrols over all possible approach routes. They needed early warning that would allow them to concentrate their limited fighters against actual raids rather than dispersing them over empty sky. Robert Watson-Watt, superintendent of the radio research station at Luftwaffe, became the pivotal figure in British radar development. Watson-Watt was a Scottish physicist with background in radio research. In early 1935, he was asked by the Air Ministry whether radio waves could be used as a death ray to destroy or disable aircraft, a concept that appeared frequently in science fiction but that physicists generally dismissed as impractical. Watson-Watt assigned his colleague Arnold Wilkins to calculate whether radio death rays were feasible. Wilkins did the mathematics and concluded that radio waves couldn't deliver enough energy at useful ranges to damage aircraft. However, his calculations suggested that radio waves might deliver enough reflected energy to detect aircraft at ranges of tens of miles. This would provide the early warning that air defense desperately needed. Watson-Watt wrote a memorandum titled Detection and Location of Aircraft by Radio Methods in February 1935. The memo outlined the basic concept: transmit powerful radio waves, detect the weak reflections from aircraft, measure the time delay to calculate range, and use directional antennas to determine bearing. The proposal was technically sound, though whether it could be implemented practically remained uncertain. The Air Ministry, under pressure to improve air defenses, authorized a demonstration. On February 26, 1935, Watson-Watt and Wilkins conducted what would become a historic experiment. They used an existing BBC shortwave radio transmitter at Daventry, a powerful transmitter that happened to be located conveniently for the experiment. They positioned a receiver in a field near Weedon, several miles from the transmitter. An RAF Hayford bomber was flown along a path between the transmitter and receiver. The receiver was equipped with a cathode ray oscilloscope, essentially an early version of an oscilloscope screen that displayed the received signal. When the bomber flew through the area, the oscilloscope showed a clear change in the received signal. The bomber's metal structure reflected radio waves, and those reflections interfered with the direct signal from the transmitter, creating a detectable pattern. The demonstration was crude. It didn't measure range or bearing accurately. It couldn't have been used operationally. But it proved the fundamental concept: radio waves could detect aircraft at useful ranges. The demonstration convinced Air Ministry officials to fund development of a practical system. Watson-Watt and his team moved to Bawdsey Manor, a facility on the Suffolk coast that would become the birthplace of operational radar. The team included some of Britain's brightest scientists and engineers: Edward Bowen, who would pioneer airborne radar; Henry Tizard, who chaired the committee overseeing radar research; A.P. Rowe, who managed the research program; and dozens of others whose names are less famous but whose contributions were equally important. The Bawdsey team faced enormous challenges in converting the crude demonstration system into operational equipment. They needed transmitters powerful enough to detect aircraft at ranges of 100 miles or more. They needed receivers sensitive enough to detect faint echoes while discriminating against noise and interference. They needed antennas that could determine direction to targets. They needed displays that operators could interpret quickly under stress. And they needed to develop all this technology in just a few years because war was approaching. The system that emerged from Bodsey was called Chain Home, a network of radar stations that would form Britain's first line of air defense. Each chain home station consisted of tall steel towers, transmitting and receiving equipment, and operations rooms where radar returns were interpreted and reported to Fighter Command. The transmitter towers were massive structures, typically around 350 feet tall, constructed of steel lattice similar to electrical transmission towers. The height was necessary because radar range depended partly on antenna height. Taller antennas could detect aircraft farther away because they weren't limited by the Earth's curvature. The towers supported arrays of transmitting antennas that broadcast radio waves on frequencies around 20 to 30 megahertz, what we would now call shortwave frequencies. The receiver towers were typically wooden structures about 240 feet tall, also supporting antenna arrays. The separation of transmitting and receiving antennas was necessary to prevent the powerful, transmitted signal from overwhelming the sensitive receivers. The physical separation, combined with electronic filtering, allowed receivers to detect the faint echoes from aircraft despite the nearby transmitter broadcasting signals millions of times stronger. The frequency choice was deliberate compromise. Lower frequencies, longer wavelengths produced better range but gave poor directional accuracy. Higher frequencies, shorter wavelengths provided better accuracy but required more sophisticated and less reliable transmitters. The chosen frequencies of 20 to 30 MHz balanced these factors, providing adequate range and acceptable accuracy with transmitters that could be built reliably with 1930s technology. The transmitted signals were pulsed rather than continuous. A transmitter would send a brief pulse of radio energy, then stop transmitting while the receivers listened for echoes. The time between transmission and echo detection directly measured the distance to the reflecting aircraft. By carefully timing these pulses, typically around 25 pulses per second, with each pulse lasting a few microseconds, the system could measure ranges with reasonable accuracy. Range accuracy was approximately plus or minus 1,000 yards, adequate for vectoring fighters toward targets, but not precise enough for pinpoint accuracy. Bearing accuracy was worse, typically plus or minus several degrees because the large antennas required for long range detection didn't provide sharp directional resolution. But the system didn't need to be perfectly accurate. It needed to be accurate enough to get fighters to within visual range of bombers, and that it could do. The display's cathode ray tubes showing the received signals required operator interpretation. Unlike modern radar screens that show clear pictures of aircraft positions, chain home displays showed oscilloscope traces that operators had to analyze to determine whether echoes represented aircraft and, if so, where they were. This required training and experience. Skilled operators learned to recognize the characteristics of aircraft returns and distinguish them from interference, weather effects, and other false targets. The stations were networked through telephone lines to Fighter Command headquarters. When a station detected aircraft, operators would telephone the information to filter room officers who collated reports from multiple stations, eliminated duplicates, and generated composite tracks showing raid size, position, altitude, and heading. This filtered information was then passed to operations rooms where controllers used it to direct fighter squadrons. Construction of the chain home network began in 1937 and accelerated in 1938 as war approached. By September 1939, when war began, a chain of stations covered Britain's eastern and southern coasts from the Shetland Islands to Portsmouth. The coverage wasn't complete. Gaps existed in the north and west, but the primary approaches from Germany were covered. As war progressed, additional stations filled gaps and extended coverage. The stations were obvious targets once war began. The tall towers were visible for miles and couldn't be hidden. German reconnaissance aircraft photographed them before the war, and German intelligence correctly identified them as radio detection stations, though they underestimated their effectiveness. The towers were relatively fragile structures that could be destroyed by bombing, but they were also relatively easy to repair. Damaged towers could be restored to operation in days, reducing their value as bombing targets. The true test of chain home came in summer 1940 during the Battle of Britain. After conquering France, Germany planned to invade Britain, Operation Salient. But invasion required air superiority. The Luftwaffe was assigned to destroy RAF Fighter Command, clearing the way for invasion. The battle that followed would demonstrate radar's decisive importance to air defense. The Luftwaffe enjoyed significant numerical superiority. Germany could commit approximately 2,500 aircraft bombers and fighters to operations against Britain. Fighter Command could field approximately 700 fighters. In traditional air warfare, this numerical advantage should have been decisive. The Germans expected to overwhelm Fighter Command through attrition, destroying British fighters faster than they could be replaced until the RAF was too weak to contest air superiority. What German planners didn't fully appreciate was how radar changed the mathematics of air combat. Without radar, Fighter Command would have had to maintain standing patrols over possible target areas, with aircraft constantly in the air waiting to intercept raids. This would have required enormous numbers of fighters because aircraft can only stay airborne for an hour or two before needing to refuel. The standing patrols would have consumed Fighter Command's limited strength, with most aircraft seeing no combat. Radar eliminated the need for standing patrols. Chain Home could detect German formations as they assembled over France. Controllers knew when raids were coming, how large they were, and what direction they were heading. Fighter Command could scramble squadrons only when raids were detected and vector them to interception points. This multiplied Fighter Command's effective strength by ensuring that most aircraft got into combat rather than being wasted on patrols over empty sky. The system wasn't perfect. Cloud cover could hide approaching raids from visual observation posts that supplemented radar. German jamming and electronic countermeasures occasionally disrupted radar. The radar estimates of raid size were often inaccurate, and altitude determination was particularly unreliable. Controllers sometimes vectored fighters to wrong altitudes or positions, resulting in missed interceptions. But despite these limitations, the system worked well enough to deny Germany air superiority. Fighter Command was in the right place at the right time, often enough to inflict unacceptable losses on German bombers. The Luftwaffe lost aircraft at rates that couldn't be sustained. German crews faced strong fighter opposition on every mission, taking constant losses that eroded both numbers and morale. The battle reached its climax on September 15, 1940, the date that Dowding was watching the plotting table with German raids approaching. The Luftwaffe launched massive raids against London, committing hundreds of aircraft in daylight attacks. Fighter Command, guided by radar, intercepted the raids with every available squadron. The air battles raged for hours, with German formations being attacked repeatedly as they approached and withdrew. German losses on September 15th were substantial, somewhere around 60 aircraft destroyed, though British claims at the time were much higher. The actual numbers mattered less than the perception. The Luftwaffe had committed major forces and failed to achieve air superiority. Fighter Command remained operational despite Germany's best efforts. Within days, Hitler postponed Operation Salient indefinitely. The invasion of Britain was cancelled. The Battle of Britain demonstrated that radar had fundamentally shifted the balance between offense and defense in air warfare. Previously, bombers had held the advantage; they could strike anywhere, forcing defenders to be everywhere. Radar allowed defenders to concentrate at the point of attack, negating the attacker's advantage of choosing when and where to strike. The technology had proven decisive in the most important air campaign fought to that point in history. While Chain Home addressed daytime air defense, Britain faced another challenge: night bombing. German aircraft attacking at night were nearly invisible. Visual detection was impossible, except on moonlit nights. Sound location was ineffective at the ranges needed to intercept aircraft before they reached targets. Night fighters attempting to locate bombers in the dark sky had almost no chance of success. Edward Bowen, one of Watson Watt's key researchers, led the development of airborne radar that could be carried by fighters. The challenge was formidable. Ground radar stations could use large antennas and powerful transmitters because size and weight weren't constrained. Aircraft radar had to be compact enough to fit in a fighter, light enough not to degrade performance, and simple enough to be operated by a single crew member while the pilot flew the aircraft. The technical requirements seemed almost impossible to meet with 1930s technology. The radar needed to detect aircraft at ranges of several miles close enough that a fighter could close to visual range before the target escaped. The radar had to distinguish targets from ground returns, reflections from the ground that could overwhelm aircraft echoes. The radar needed to show bearing to the target so the pilot could steer toward it. And all this had to be accomplished with equipment weighing less than 200 pounds, operating on the limited electrical power available from aircraft generators. Bowen's team worked through multiple iterations, gradually improving performance and reducing size and weight. The first experimental systems, tested in 1937, were crude but demonstrated that airborne radar could detect other aircraft. By 1939, more refined systems were being tested operationally, though reliability remained problematic. The breakthrough came with the development of the cavity magnetron in 1940. This device, invented by John Randall and Harry Boot at the University of Birmingham, could generate powerful microwave signals, much higher frequencies than chain-home used. The shorter wavelengths allowed much smaller antennas while providing better resolution. The cavity magnetron made practical airborne radar possible. The AI Mark IV radar, introduced in 1940, was the first operationally successful airborne intercept radar. It could detect aircraft at ranges up to 3 miles, providing enough warning for night fighters to intercept bombers. The system consisted of transmitter and receiver units, antennas mounted in the aircraft's nose, and a display showing range and bearing to the target. A radar operator sat behind the pilot, operating the radar and directing the pilot toward contacts. The Bristol Beaufighter became the primary RAF night fighter once equipped with AI radar. The Beaufighter was fast enough to catch German bombers, had long enough endurance for extended patrols, carried heavy armament, and had room for the radar equipment and operator. With AI radar, Beaufighters could patrol over Britain at night and intercept German bombers attempting to strike cities in darkness. The tactics were revolutionary. Ground controllers using chain-home would vector Beaufighters to intercept German bomber streams. Once the night fighter was within a few miles of the bombers, the AI radar would detect them. The radar operator would guide the pilot onto the bomber's tail, closing the visual range typically 500 to 1,000 feet. At that range, even in darkness, the bomber was visible enough for the pilot to aim and fire. The engagement would be over in seconds, with the bomber shot down before its crew even realized they were under attack. The effectiveness improved dramatically through 1941 and 1942. German losses to night fighters increased from negligible to substantial. Bomber crews that had operated with relative impunity in darkness now faced lethal opposition they couldn't see until tracers announced the attack. The psychological impact on German bomber crews was severe. Flying missions knowing invisible fighters could attack without warning eroded morale more than predictable daylight opposition did. The Germans responded with their own radar developments and countermeasures. German night fighters began receiving radar equipment, initially for defense against RAF bombers attacking Germany, but eventually for offensive operations as well. The technology race between radar and counter-radar became defining feature of the night air war for the remainder of the conflict. The United States began radar development slightly later than Britain, but eventually surpassed British capabilities through enormous investment of research and industrial resources. American radar development benefited from British sharing of technology, including the cavity magnetron, which the British provided to the Americans in 1940 despite it being one of the war's most closely guarded secrets. The Radiation Laboratory at MIT, established in 1940, became the center of American radar research. The lab eventually employed over 4,000 people, including many of America's top physicists and engineers. The scale of the operation dwarfed British radar research and allowed parallel development of multiple radar types for different applications. American research focused on improving performance and reliability while reducing size and complexity to facilitate mass production. British radar systems, developed under wartime urgency, often prioritized getting something working over elegant engineering. American researchers had slightly more time and much more resources, allowing development of systems that were more sophisticated and more manufacturable. The SCR-584, developed for anti-aircraft fire control, exemplified American radar excellence. This ground-based radar automatically tracked aircraft and provided aiming information for anti-aircraft guns. The automatic tracking the radar locked onto a target and followed it without operator input represented substantial advance over systems requiring manual tracking. The SCR-584's accuracy allowed anti-aircraft guns to engage targets effectively even at night or in poor visibility. American airborne radar development produced systems for fighters, bombers, and patrol aircraft. The -720 Seychelles rupees, developed for night fighters, provided better range and reliability than earlier British systems. American night fighters like the P-61 Black Widow were designed from the outset to carry radar, with dedicated radar operators and carefully integrated systems. The P-61 became one of the most effective night fighters of the war. Bomber radar included systems for navigation, bombing, and defense. The H-2X radar allowed bombers to navigate and bomb through clouds and darkness, using radar images of the ground to identify targets. The H-2X was particularly valuable in European theater where cloud cover often prevented visual bombing. The ability to bomb through clouds meant that strategic bombing could continue regardless of weather, dramatically increasing operational tempo. Naval applications of radar were extensive. American warships received increasingly sophisticated radar systems for surface search, air search, fire control, and navigation. By war's end, even relatively small vessels like destroyer escorts had multiple radar systems, providing capabilities that wouldn't have been imaginable pre-war. The radar-equipped U.S. Navy could fight effectively in darkness and poor visibility, advantages that proved decisive in Pacific night battles. The mass production of radar equipment was itself a remarkable achievement. American industry produced hundreds of thousands of radar sets of dozens of different types. The manufacturing required precision electronics assembly at scales previously unknown. The training of personnel to maintain and operate this equipment required educational programs that processed tens of thousands of technicians through compressed curricula. The logistics of distributing radar equipment worldwide and keeping it operational under field conditions challenged supply systems but ultimately succeeded. German radar development followed different path than Allied programs, shaped by different strategic priorities and ultimately by Germany's deteriorating military position. Germany had radar technology comparable to Britain's in the late 1930s but didn't pursue it as aggressively because German military doctrine emphasized offense rather than defense. The Freya early warning radar, deployed in 1940, provided similar capabilities to British chain-home detecting aircraft at ranges of 80 miles or more. The Wurzburg fire control radar provided precision tracking for anti-aircraft guns and ground-controlled intercept of fighters. By early war standards, German radar was technically sophisticated and operationally effective. As the strategic situation shifted and Germany was forced onto defensive, radar became more important. The Allied strategic bombing campaign against Germany, beginning in earnest in 1942 and intensifying through 1943 and 1944, required German defenses to develop radar-based detection and intercept systems comparable to Britain's. German night fighters received radar equipment for intercepting RAF bombers attacking German cities. The Liechtenstein radar, German airborne intercept radar, underwent continuous development as countermeasure and countermeasure competition intensified. Allied electronic warfare efforts to jam or deceive German radar forced constant modifications. German scientists developed new radar types using different frequencies or techniques to evade Allied countermeasures. The technological competition drove innovation on both sides but increasingly favored allies who had more resources for research and development. German radar also faced industrial limitations. The precision manufacturing required for radar components competed with other military needs for skilled labor and materials. As Allied bombing damaged German industry, radar production suffered along with other equipment. Quality control degraded as experienced workers were conscripted and replaced with forced labor. Radar sets became less reliable, creating maintenance burdens that German technical services struggled to meet. The strategic bombing of German radar sites became priority for Allied air forces. Radar stations were targeted to blind German defenses before major bombing raids. The stations could be rebuilt, but the continuous attacks created gaps in coverage that Allied bombers exploited. The erosion of German radar coverage paralleled the general decline of German air defenses through 1944 and 1945. Parallel with radar development came electronic warfare efforts to jam, deceive, or otherwise interfere with enemy radar. This invisible battle became as important as the visible air combat, though it received far less attention from historians until decades later. The British began systematic radar jamming in 1942 jamming. Transmitters broadcast powerful signals on frequencies used by German radar, creating noise that obscured legitimate returns. The jamming could blind radar completely if powerful enough, or could reduce its effective range and accuracy if less intense. German radar operators learned to recognize jamming and develop techniques to work through it, but jamming remained effective countermeasure. Window strips of aluminum foil cut to lengths that reflected radar energy was perhaps the most effective radar countermeasure of the war. When bombers released window, the falling strips created thousands of false radar returns that overwhelmed German radar screens. Controllers couldn't distinguish real aircraft from window, making it impossible to vector fighters to intercept bombers. German night fighter effectiveness dropped dramatically when RAF Bomber Command began using window in July 1943. The Germans developed countermeasures to window, including radar systems operating on different frequencies where window strips were less effective, and airborne radar with discrimination capabilities to filter out window returns. The British responded with improved window designs and tactics. The cycle of measure and countermeasure continued throughout the war, with each side seeking advantages that might last weeks or months before being countered. Radar homing missiles represented another application of electronic warfare. German scientists developed the Enzian anti-aircraft missile guided to targets using radar. The weapon was never deployed operationally, but it pointed toward future where radar would guide missiles to targets autonomously. Allied researchers pursued similar concepts, though none became operational before war's end. The technical sophistication of electronic warfare by 1945 was extraordinary compared to 1940. What began as simple jamming evolved into complex systems that identified, analyzed, jammed, and deceived enemy radar using techniques that anticipated Cold War electronic warfare. The specialists who operated these systems, electronic warfare officers on bombers, radar operators analyzing enemy signals, scientists developing new countermeasures, were fighting battles as important as the pilots flying aircraft, though their battles were invisible except on oscilloscope screens. Radar played different but equally important roles in Pacific theater. The vast distances, island campaigns, and naval warfare created unique radar requirements that drove different developments than European warfare. Naval radar was perhaps more important in Pacific than Europe because so much combat occurred at sea. Radar allowed naval forces to detect enemy ships and aircraft at ranges exceeding visual detection by tens of miles. Night battles that would have been impossible or suicidal without radar became tactically viable. The Battle of Cape Esperance, the Naval Battle of Guadalcanal, and other engagements were fought largely by radar-directed gunfire in darkness that made visual aiming impossible. American carrier forces used radar for air defense and fighter direction. Radar-equipped carriers could detect Japanese air raids while they were still dozens of miles away, providing time to scramble defensive fighters and position ships for maximum defensive firepower. Fighters could be directed by radar-based controllers to intercept raids before they reached the task force. The effectiveness of American carrier air defense improved dramatically through the war as radar systems, and their operational employment were refined. Airborne radar proved valuable for patrol aircraft searching vast ocean expanses for Japanese ships and submarines. PBY Catalinas and other patrol bombers equipped with radar could search far larger areas than visual observation allowed. Submarines detected by radar faced attacks they often never saw coming. The radar-equipped patrol aircraft became a major threat to Japanese maritime traffic, contributing to the blockade that strangled Japan's economy. Island campaigns used radar for air defense and fighter direction much as in Europe. Islands seized from Japanese control quickly received American radar installations that provided early warning of Japanese air attacks. The radar allowed fighter controllers to direct combat air patrols to intercept raiders, improving kill ratios and reducing damage to ground installations. The radar installations became high-priority targets for Japanese counterattacks. Japanese radar development lagged behind Western efforts, handicapped by less advanced electronics industry and insufficient resources for research. Japan deployed radar systems that were adequate by early war standards but fell progressively behind as Allied systems improved. The gap contributed to Japan's declining air and naval effectiveness as the war progressed. Japanese forces increasingly fought without the situational awareness radar provided to their opponents. The wartime radar developments revolutionized civilian and military applications after 1945. Technologies developed for military needs found widespread civilian use, transforming aviation, navigation, weather forecasting, and eventually creating entirely new industries. Commercial aviation adopted radar for air traffic control and aircraft navigation. Before radar, air traffic control relied on visual observation and pilot position reports methods that limited traffic capacity and were unsafe in poor visibility. Radar allowed controllers to see all aircraft in controlled airspace simultaneously, dramatically improving safety and increasing capacity. Modern air travel wouldn't be possible without radar that traces lineage directly to wartime development. Weather radar transformed meteorology. Radar could detect rain, snow, and other precipitation, allowing forecasters to track storm systems and issue warnings. The basic technology was identical to aircraft detection radar. Both detected reflections from objects in the atmosphere, but weather radar interpreted those reflections to map precipitation intensity and movement. The weather forecasting revolution of the post-war decades depended fundamentally on radar. Military radar continued rapid development through the Cold War. New applications emerged. Airborne early warning radar detecting low-flying aircraft from above. Over-the-horizon radar detecting targets beyond line of sight. Phased array radar that could track hundreds of targets simultaneously. The radar systems on modern military aircraft are so sophisticated that they're essentially computers that happen to emit and receive radio waves. The scientific and engineering expertise developed during wartime radar programs influenced post-war physics and electronics. Many radar researchers continued careers in electronics industry or academia, applying knowledge gained during war years to civilian applications. The techniques for generating high-frequency radio waves, processing weak signals, displaying information clearly, and integrating complex systems all found post-war applications far beyond radar itself. The cavity magnetron, developed for radar, became key component in microwave ovens, one of the most direct transfers of military technology to consumer products. The same device that allowed detection of aircraft at night eventually enabled reheating leftovers in minutes. The example illustrated how wartime necessity drove innovations that transformed post-war civilian life in unexpected ways. Behind the technical achievements were thousands of individuals whose contributions enabled radar's success. Some became famous. Watson Watt received knighthood, and many senior researchers received recognition, but most remained obscure despite important contributions. The scientists and engineers who developed radar often worked under enormous pressure. Lives depended on their work succeeding. Failure meant prolonged war, more casualties, possibly defeat. The stress of working with these stakes, combined with long hours and difficult technical problems, tested everyone involved. That they succeeded was testament to their skill, determination, and commitment to the cause. The operators who used radar in combat, radar plotters tracking incoming raids, fighter controllers vectoring interceptors, shipboard radar operators, detecting enemy vessels performed demanding work that required intense concentration, often maintained for hours under combat stress. Their performance directly affected battle outcomes. Mistakes cost lives. Excellence saved lives. The responsibility was enormous. The maintenance personnel who kept radar systems operational under field conditions performed essential work that rarely received recognition. Radar was complex, delicate equipment prone to failure under harsh conditions. Keeping systems working required technical knowledge, dedication to maintenance, and creative problem-solving when proper parts weren't available. The maintainer's unglamorous work was as essential as the designer's innovations. The Women's Auxiliary Air Force members who plotted radar returns in fighter command operations rooms were crucial to the integrated air defense system. Their careful plotting of raid positions and movements provided controllers with situational awareness necessary to direct fighters effectively. The women performed demanding work with precision under stress, knowing that pilots' lives depended on accurate information. Their contribution to the Battle of Britain was substantial, though often overlooked. Radar's strategic impact extended beyond its direct military applications. The technology influenced grand strategy, shaped campaigns, and affected the war's outcome in ways that weren't fully appreciated until decades later. The Battle of Britain was won partly because radar allowed Fighter Command to husband its limited resources and concentrate at the point of attack. Without radar, Fighter Command would likely have been overwhelmed by attritional warfare that Germany intended. The survival of Britain as base for future operations against Germany was enabled by technology that existed only in laboratory form 5 years earlier. The strategic bombing campaign against Germany was made possible partly by radar. Bomber Command could attack in darkness and through clouds, capabilities that depended on radar navigation and bombing systems. Without radar, strategic bombing would have been limited to daylight attacks in clear weather conditions that would have made losses unsustainable. The sustained pressure that strategic bombing applied to Germany depended fundamentally on radar technology. The Battle of the Atlantic was influenced by radar that allowed aircraft and ships to detect U-boats on the surface. Submarines forced to remain submerged by radar-equipped patrol aircraft were slowed and had limited operational capability. The radar contributed to Allied victory in the Atlantic, though how much is difficult to quantify precisely. Naval warfare was transformed by radar that allowed forces to fight effectively in darkness and poor visibility. Surface actions between American and Japanese forces in the Pacific often involved radar-directed gunfire at ranges where visual aiming was impossible. The night battles would have been chaotic knife fights without radar. With it, they became calculated engagements where radar-equipped forces held enormous advantages. The closing years of the war saw radar so integrated into military operations that forces without it were severely handicapped. Japanese forces lacking effective radar faced opponents who could see them long before they could return the favor. German forces in 1945, with degraded radar coverage due to bombing and equipment shortages, struggled against Allied forces whose radar capabilities continued improving. The technological asymmetry contributed to the speed of Allied victory once Germany and Japan were on the defensive. The handful of radar pioneers who changed air combat forever accomplished something remarkable. They took theoretical concept and transformed it into operational technology that fundamentally altered how wars were fought. The journey from Watson Watt's 1935 memo to sophisticated radar systems guiding fighters, directing bombers, and coordinating naval battles took less than 10 years, a pace of innovation that seems barely credible even today. The pioneers themselves were ordinary people in extraordinary circumstances. They were physicists who became engineers, academics who became military advisors, and visionary officers who recognized technology's potential before it was proven. They worked under pressure with inadequate resources against tight deadlines, knowing that failure meant disaster. They succeeded through intelligence, persistence, and occasional luck. The technology they created saved countless lives by allowing defense to match offense in the air. Fighter Command's victory in the Battle of Britain, achieved partly through radar, prevented German invasion and kept Britain in the war. Night fighters guided by radar stopped German bombing campaigns that might have forced Britain to negotiate. Allied bombers using radar navigation and bombing systems maintained pressure on Germany that contributed to ultimate victory.